All right, welcome everyone. So welcome back to this rather special lecture. So first of all, I'm sorry I have I got a throat ache today, so my voice is a little bit strained, but never mind. We will go through this. And so today, since we're very good in time, so this is unusual for me. So what we're gonna do is we're gonna try, and these were some comments from the evaluation of the last summer term. Where couldn't we prepare a little bit more towards the exam, like not only understanding, but also some calculation? And surely we should do. So we should do both, strengthen your understanding and then see what kind of calculations will help you to strengthen this understanding. And today we will do both. So it's a little bit of a special lecture. It's approximately an hour, and then we have time for Q&A. I think it's needed. And as I said, this will be recorded. So if you're watching at home, welcome also if you watch this later. So before we go into all the details and continue our path, let me explain what we're going to do today. So today we're going to do three things, right? So we're going to finish in general understanding what these types of layers do, right? So we actually started with the convolutional layer and we said, okay, this is what the convolutional layer does. And we had some calculations that I also showed on the Blackboard, and we will strengthen our understanding. So this is the first thing today is we're gonna continue understanding, right? Understand layers. This is what we want to do. The second is we want to see what are the calculation in the layers, right? So after we understand generally without calculation, we want to understand the calculation, right? And third, we want to understand a little bit about sizes and parameters. Sizes plus number of parameters. And this is something special. I put this in because it's a very cool thing I could ask you in the exam because it's very easily calculated, but you have to think a little bit about this. And also, so it's not only for the sake of the exam, but also this will help us to compare it to the approach that got us to the CNN, applying an ANN throughout the whole thing. We know that this is not feasible, and here we will see why. We will see that we have a lot less parameters to train than if we would use an ANN, right? So actually, this shows that we kind of achieved what we were actually looking for. So, okay, so again, so we have four types of layers, of basic layers. So I added this a little bit because as time moves on, there are other techniques that go into this and other architecture designs. So basically we have the convolutional layer. Like this is the most important layer, okay? Like this is the layer that does all the heavy lifting. This is the layer where we said, okay, this is where we actually inspect the image, right? And this layer has neurons, and each neuron is called a filter, and the filters are looking for specific things. Like they are looking for squares, or they are looking for just these or these, or something like this. So this is every filter looks for specific things, and then on top of this we can build other filters, right? And then we get more complex. So this could be the first layer, and then we do all the other layers. And we have the second convolutional layer, and this could maybe something like this. So we want to have where this is these two things together, maybe, right? And then maybe also with this. And so we can build a car or something out of it, right? So and this goes on. So we build more complex things as we move along. This is the basic idea. So the convolutional layer is what does that, right? So all the other layers here, like specifically these two layers, the next to the pooling layer and the ReLU layer, they are kind of a package. So I want you to think it's easiest to think of these as some kind of a package deal with the convolutional layer. So these are kind of a package here. They are not always like applied together, but usually they are, right? So this is kind of a package deal. And you can see here, they are packaged together, and then there are these three dots because now we can put more convolutional ReLU pooling packages in there, and we will do a lot. Like this is not that we only lose one convolutional layer, then a ReLU, then pooling, and then a fully connected layer, right? So we will have a lot of these packages after another to achieve this, right? Simple forms, more complex forms, and in the end, we want to detect something like a phase, like in this example, which is a very complex form, and it has multiple forms that need to go together. Okay, this is the idea so far, okay? And so I want you to think of these as a package, and it's easy to understand. Once we know what the convolution layer does, the other two are fairly simple. Like, as I said at the beginning, when I said, hey, why can't we use ANN? Because it's too large, right? We have images and the image size is too large. We have many input layers, then everything is fully connected all the time. So this is a problem, right? So then the idea of a CNN was that we basically split the CNN in an image generation, like this is a feature generation thing. Like image, I'm gonna call it image feature generation. Image feature generation. And these are all the packages of convolution, value pooling, so all the new things that you learned basically, right? And like this also includes these 3 points, like also everything. And then at the end here, we have one last layer, like it might, for example, be a value or a pooling layer, and it has a certain size. And it puts out feature maps, just like the convolution layer puts out feature maps. It's always the same, right? There's nothing different. And then we're going to use the fully connected layer, which we're going to explain in a few minutes. And the fully connected layer actually is the classification, right? Is the classification. This is like we put a classification model onto these features that we extracted. But again, since we're in deep learning, we let the computer do the heavy lifting for us. So we are not concerned with extracting all these features here, right? We are not extracting these features. Like we want the computer to do this, right? So we're not extracting all these complex features here. The computer does it for us. And in the end, we put them into a normal neural network. So what is fancily called a fully connected layer is just a normal ANN with either one or more hidden layers. Now we can also choose hidden layers. And in the end, in step number 3, I will have a nice table that suggests a small CNN, and we will see how it could work. Okay, so don't worry about it. So the convolution layer, right? So again, we use the simple example with the X. So our input image is very simple. It's the simplest form, it's the simplest thing it can be. Like we will have more complex examples later on. So we have -1 and 1. Whenever it's white, it's 1. Whenever it's black, it's -1. It's that simple, right? So this is the input image, right? And we can see the dimension of the input image. Also, we can count 1, 2, 3, 4, 5, 6, 7, 8, 9 times 9. So it's 9 times 9. And of course, how many channels do we have? Only one channel, right? So this is not RGB. We only have one channel. It's only black and white. So we don't need 3 channels as an RGB. So basically the dimension we're going to use, usually this is the notation, right? So these things are usually noted in basically the width, the height, and the depth, right? So how many channels do we have? So the first is basically 9, 9, 1, right? So this is the dimension of the image, okay? So 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay? So 9 times 9 and only one channel. So, and this is like how we can, so if you see this could also be the exam. Like I give you and say, hey, describe it in that tuple, right? So you know, okay, 9, 9, 1. Okay. Easy. Now, if this was RGB, this would be free, right? But we will see this. Okay. Now, the first thing we went through is the convolutional layer. Now, the convolutional layer has filters. Like the neurons of the convolution layer are filters. And the filter look like this, right? This is a filter. So the filter has a size called the receptive field, and the spatial extent of the receptive field is determined by a hyperparameter called f, right? And f is like, this thing is f times f, right? The size is f times f. So it's 3 times 3, as we see. So f equals 3 in my case here. So, and each value in here, all these values here, they are parameters. So they are trained by the CNN or by the learning algorithm that trains the CNN, right? So this is very cool for us. So I'm going to put a smiley. because we don't have to care about this, right? So this is a thumbs up from us. This is pretty cool. So if I ask you, where do you get these values? How do you set these values? You remember on the blackboard, I said you don't, right? So this is just what's straight, okay? And then we layer this above the original image. Now remember, this is our original image, right? And we're gonna start here. So it's a 3 by 3. So we're gonna start here. And then we multiplied each value with the value of the matrix, right? So as you see here, so we multiply this -1 here with the -1 of the filter. So this is another position here. And what we get is an intermediate result. And then what we're gonna do is we're gonna add up all these results and do two things. So either we're gonna divide it, we just add it up. So here it would be 9, right? So this would be 9, and we can divide it up by the number of values, like it's by the number of the size of the receptor field, which is 9, or we could just add them up. So there's a discussion, or there are many ways of doing this. Usually it's added up. In this case, we directly divide it. Now, usually these are just added up because what we do is after the convolutional layer, we do what is called a batch normalization, which just is a normalization. It's a set normalization where we get from one batch. Remember, a batch is a part of the training data set. And we just for the pixels, we just calculate the average and the standard deviation, and we do a set transformation. So the batch normalization is just a set transformation of all the values, right? It's a set transform of all the values. And why do we do this? Well, to keep it in check, to don't get large values, largely different magnitude of values. And this is a great thing because our optimization will be better and faster. So this guarantees us faster convergence, right? Faster convergence. So we can actually also choose a larger size alpha, larger learning rate, right? With this. So you can think of a batch normalization as just doing the normalization. So it doesn't really matter. So also in the exam, if you do this, or if you add it up, I don't care, right? So in this example here, it's divided, just so you know. Okay, don't worry, we will have in the second step here, we're just in the first step. In the second step, we will do calculations. So we're still in the first step, right? Okay, so we're gonna look, and then what we get, and this is the most important thing, we get what's called a feature map, right? And the feature map indicates for each filter, this is the result of the filter application onto the image. And we see, okay, if there's a large number, that means, hey, what we were actually looking for is in the image, right? And here it makes sense. You can see now this filter detects this shape, right? It detects this shape. So if this is our vector, we're looking for this shape. So we're looking for diagonals from top left to bottom right, right? So for these kind of diagonals in the image. And as you can see here, in this part of the image, there is exactly this diagonal present. It's the upper left part of the X, right? So this is present here. So that means that we say, hey, we've actually detected this, right? And it's surrounded by black. This is exactly what we want. So, and if you want a logic for this, so while these are parameters here, it's pretty easy. We can see, okay, we only want the main diagonal to be white, and the rest needs to be black. Because actually, we don't want these to be white. So we set this -1, and -1 times -1. So if it's black in the image, that's good. We get a large value, right? And if this is 1 in the image, then that's great. We get a large value, right? And that's the idea. So we get a maximum value of 9. And you can see we get the value of 1 here in the feature map. This is the respective value here of 1 in the feature map. Okay. Sorry. And this is basically the idea. So the feature map is really a map of the image. So it's not it's really like a heat map. You can think of it as a heat map or a report card. We told you this is a report card and says, hey, at this kind of location. So we also have the location, right? It's pretty important that we have the location. So we can like have this here, or we can have this. We also have this here, right? So it doesn't matter. The filter just detects the thing. And the feature map says where. So this is also an important thing that we cannot have an A and N because it's interchangeable, right? And here we can basically say, hey, there is a diagonal and here's a diagonal and so on. So this is pretty cool. So this is a feature map for detecting this kind of shape, right? Okay, pretty cool. And then again, we have multiple of these filters in one convolutional layer, right? So this is just one filter, but we can apply a lot of other filters. And yeah, we discussed this. So this is rather important that you understand what kind of hyperparameters are there. Like what do we need to know? What do we need to set? And let me quickly go through. So what we have, so you always need to know for each layer, what's the input, like what goes into the layer. And usually what goes into the layer in convolution is always a thing. I'm just saying a thing that looks like this, right? For the first convolution layer, the thing is the input image, right? So in our case, this is 9, 9, 1, right? This is the input, right? This is the input. The input could be anything. Like you remember our the example web page I gave you, the CNN explainer, I think it has 64, 64 and 3, right? So or 62, 62 and 3. So this dimension, this is the input of the layer. So this is before anything happens. And then what we do is we have a number of filters. So in this is the number of neurons that we have. So how many different things we are looking for, right? And each filter has a receptor field. Now the receptor field is always the same for each K, right? So that doesn't change. It's very simple. So it's always, if here in our case, I'm going to write it in green. In our case, this is 3, right? So the stride equals 1. Zero padding is, we will explain what zero padding is right after the slide. So don't worry about it. In this case, we have no zero padding. And then it produces the output. This is the feature map. So the output is the feature map, right? Of this size, right? And that's basically it, right? And we also have the number of parameters, but we will go through this in step number 3 that we do today. So the calculation will follow, right? But you can read it here. Sorry. Yeah. So moving on from the understanding is the next thing is a pooling layer. And the pooling layer, the job of the pooling layer is very simple. It's to reduce the size. Like usually with the convolution, we want to keep the original input size, or with the first convolution, or at least be near it. So we don't actually in the convolution layer. Usually, this is why we have a stride of 1, for example. A stride of 2 would halve it, right? So because you can see here the size is it's divided by s, which makes sense. If you move double the pace, you miss half the reports and the fields in the report card, right? And so, but the problem is if we keep this up, we still get a pretty large network, right? We still get pretty large outputs. We have to save the outputs in the RAM, right? Which affects our run through, which is our inference. So when once we have a productive system of this thing, remember we have quality assurance where we have multiple cameras in every process step, and we only have like 1 second, and this takes too long because it's not fast enough because we have these large image maps and these large multiplications. So multiplications get more complicated because we have larger matrices and so on, larger tensors. So it just makes sense to just reduce it and say report the most important things. And so this is where the pooling layer comes. And as I said, the convolution layer does all the heavy lifting. Like the convolution layer identifies the thing. So this is the basic need. Everything that comes now, so the pooling and the ReLU just makes it easier for the network. It makes the network smaller. So I want you to think of this as helper layers, right? So, and this is why they are fairly easy. And also, this is why they don't have any parameters learned. So the only parameters that are learned are in the convolutional layer. This is very important. And I'm talking about parameters, not hyperparameters. Like these are the parameters that are learned. That's it, right? And the bias, of course. But we will talk about this in a second. In the pooling layer, there are no learnable parameters. There are only hyperparameters. And they are basically the same as in the convolution layer. So again, the pooling layer, as you can see here, so the red thing and the yellow thing, they also have hyperparameters and they also have an f, right? They also have the size f times f, and in my case, it's 2 and 2, as you can see here, 2 pixels in the example. And now they also have a stride, and in my case, and this is usually 2, since we want to make it smaller, the stride usually is 2, right? Or in this case, it's 2, and you can see it here. It doesn't move 1 pixel, but it moves 2 pixels. This is why the yellow frame is 2 pixels apart from the red frame, right? And then within these frames, we have 4 values, right? 2.2, right? 2 times 2. And what the pooling layer does is it looks for them, and the pooling layer, actually, in this case, is so-called max pooling layer, and it just filters the maximum value. That's all we're looking for. Since we only want to see, hey, is there something? Because if there's nothing, that isn't really interesting for us, right? So we want the max. So we look at all 4 values, and then we just report the max. Then we shifted the yellow thing, and we report the max. Then we shift it again. I'm going to do it, right? You can see the green thing here, and we report the max, which is 0.55. And then, right, I'm going to use another color to make sure, to make sure you see it. We're going to use not red, we're going to use blue. And then, and this is very important, it doesn't end here. Now, here you see, yeah, but Kai, what the hell? This is not. Yeah, we just, oh, it's green again. She wanted blue. Sorry. So yeah, what the hell? Yeah, but then we continue. So it doesn't really matter that there's nothing here. Like, so we just look at these 2 values, but we have to include them, right? It moves, but it moves like this, okay? And it doesn't really matter, right? So this is how we can deal if the dimension is not a number is divided by 2, right? Okay, so it's an odd number. If it's an odd number, it doesn't really matter. And here we do the same, and you can see it's 0.33. And then we move again, and now you think, how do we move? The same. We move the stride is not only for the horizontal, but also for the vertical. So let me again have, I hope I have another, but it will be the last. I have another color. Yeah, let's lose this color. Okay. Then we're going to move again, and here we see, yeah, you can see the purple one, right? And the purple one, you can see here, is right here. Yeah, and 0.33 is the max in the purple one. And if you want, you can like continue this, but it's fairly simple, right? And we do the same thing. And of course, then we're gonna go here. And here it's by the way the same thing. I'm gonna do one last thing. I think I don't have any more colors left, but let's look here. And here it's the same thing, right? So we take this and we take the max here, although you see here that it's not like we don't have these, right? Doesn't matter. Okay. And this is just the pooling layer just reports back the max. So we see now we have a report card that's smaller, but still has the most important things here, right? That's basically it. That's all the pooling layer does. So the important thing that you have to think about is, hey, so when I tell you all these things, the important things that you need to remember, or that you need to, like, after the lecture go through, is what are hyperparameters that you need to set, and what are parameters. So a lot of these layers don't really have parameters. They only have hyperparameters, right? Like here, we only have hyperparameters in the pooling layer. So the next one is, so again, these are like the hyperparameters, and you can also, like, it's the same formula, like you can do the same thing, right? In the pooling layer, we don't have zero padding, right? So there is no zero padding. So P, you can also, it's the same formula with P always 0, right? So this is why I usually use it in the formula, but it's actually always 0. We don't have zero padding there. Okay, the ReLU layer is pretty cool. The only thing the ReLU layer does is it again helps us to have less calculations. right? So as I said, we're only interested in large values because what we do is the convolution layer, which does all the heavy lifting, the filter looks at the image and says, hey, there is something. We are not interested if there's nothing. So if it's nothing or really nothing, we don't care. So you can see here all these negative values like these, right? We don't really care if this is minus 0.11 or minus 20 or whatever. We don't care, right? And the problem is, if we continue with that, and as I said, these values will be multiplied again with other values. So there's a lot of tensor and matrix multiplication happening in CNN and also in the inference. And we don't want that. We simply don't want that. We want easy multiplication. So what we do is we just have the ReLU, we just apply the ReLU layer, which just checks every value. So it's a pointwise operation. Again, checks every value. Hey, if the value is larger than 0, then it just keeps the value, right? Value, then value. And else, if the value is smaller than 0, right? So it's basically, or smaller equals 0, it's basically 0, right? You can see here, it's the max of 0 and x, right? So this is the function. So it's max 0x, so this means it's either 0 or it's the value. And that's it, right? So what kind of advantages does it have? Well, have you recently multiplied things by 0? What's the result if you multiply things by 0? You know this, right? It's always 0. So there is no calculation needed. That's the beauty. So all these black thingies here, you see these? You save computation. You save computation. It's that easy. It's just that easy, right? Are those empty values 0 or just max out of 2? Stelios has a question. I think this is for this one right here, right? Stelios. You mean these empty values here? No, it's the max out of the 2 values. They are not 0. It's the max out of the 2 values. Yeah, sorry. There are no values. Like we don't put a 0 here. If we put a 0 here, that's called 0 padding. We will go through that in a second. So there was just a question if we set these values to 0. No, we just take the max out of these 2 values, right? Sorry for not clarifying this. I just saw the question chat. Okay, the fully connected layer. After we've done all this shenanigans, so as I said, we repeat a lot of convolutional layers. So convolutional layers, max pooling, ReLU, right? There's also debate on, we can also change this. So specifically, we can put the ReLU before the max pooling. So it's easier with the max operation. So it just sometimes saves us a little bit computation to do it the other way around. But there's a discussion. I've linked at this discussion forum in the lecture notes. So if you want, you could read about it, right? So this is really your choice, right? And so this is usually our package, right? So this is called package 1. And then we have package 2, and each package is like these layers, right? And we have package 3, package 4, and at some point after package 4, so package 4 basically ends with feature maps, like package 4 ends with feature maps, then there is a fully connected layer, right? It can also be more than one fully connected layer, right? So so let's make it more complex for you, okay? Okay. So, and as I said, this is basically image feature generation, and this is basically classification, because the output here is the class, boat, face, whatever, right? Yep. So, and package 4 looks like this, right? Package 4 looks like this. So we have all these feature maps here that have some dimension, whatever they are, right? So we have, let's say we had two filters here, right? We had 2 filters in the last convolutional layer. Then we applied max pooling. So we have 2 feature maps, applied max pooling. Then they got smaller after max pooling. Then we have ReLU. So we have some zeros in there. they keep their size in value, obviously, right? So only max pooling changes the size. And then what we do is we flatten these out. So this value gets on. So we have a large input vector, right? And this value goes here, this value goes here, and so on, until this value goes here, right? So we just flatten them out in a vector. And now what we can do is we can build a simple neural network that you all know, and they are all fully connected, right? As you know it, this is how it works, and this is the fully connected layer. So basically, we cheat a little bit. We say we can't really use a neural network for all the feature extraction. So we have cooler tools with all the convolution layers, but in the end, we need something to actually classify it. So we need actually classifier that considers all these features that the package 4 pumps out, right? So we need to consider all these features. And then we just simply say, hey, and now we can use an ANN, right? And this is simply how it works. So I want you to think of it as CNN if you split it up in 2 steps. So first we generate features out of the image, and then we do normal classification. It's easier to understand. And this is how a CNN works. And that's it, right? So that's usually it. As you see here, we repeat a lot, right? And then we get simply numbers right here, and that's it. That's simply it. Okay, so what we now want to do is, so this is just a general idea, which is pretty cool. So this we have done, and now we're gonna go to calculation, right? So, and for this, what I'm gonna do is I'm gonna share my, I'm gonna share my zero padding. No, this is not the one. This is not the one. Wait, this was ChatGPT explaining to me what zero padding is. Let me just see where we have it. Here. This. Okay, this is the right one. So, okay, let's see. Just a second. Here we go. This should be it. Okay, this should be it. You just see, yeah, okay, this is it. Sorry, I have so many windows open. Okay, now I promised you to explain what zero padding is, right? So as you saw in all the formulas, there's this P, right? Which I always said, oh, it's zero, blah, 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 which is pretty cool, but what actually is zero padding, right? So just a second here. So what actually is zero padding? And it's pretty simple. So what I'm gonna start with is we're going to start with the usual input, right? And with the filter, and then we're going to calculate the output to see the effects, right? This is pretty cool because we're already practicing calculation. So we're going to go towards what we actually want. We're going to go to calculations. Okay. Now, what we have here is we have an input image, right? So this input image here, right? Let me just look another. I shouldn't use white. Doesn't make sense. Okay, so this input image here, right? And this input image, as you can see, is width and height is 4, right? You can see it's 4, a bit larger here, so you can see it. So, and this is 4, and it has some values in it, right? So, and this doesn't have to be an input image, right? It could also be just a feature map, like for subsequent layers. So the important thing is that it doesn't really matter if it's an image or it is something else. It's important that it's just a matrix where there's some values in it and it has a certain size. We can always apply the filter onto that, right? And obviously in subsequent layers, we are not applying it to the image, but to the feature maps, right? So, okay, we have the input image or feature map. This is why I put this slash in here. So we have the width and the height is 4, right? So the width and the height is 4. You can see it's a 4 by 4. 1, 2, 3, 4, 1, 2, 3, 4. Can just count it, okay? It's not really hard. Okay, so in this case, we have no zero padding. So what we always say, we don't know what zero padding is. So what the hell, okay? So it's 0. Now we have this really cool formula, which just says, okay, what is the size? And the size is pretty easy. So the formula explained, this is a very important calculation. So what's the output size? And the output size is is output width and height. So width and height is usually the same. So we just need to do it for one of them. So with feature map, I'm gonna call it with feature map is height feature map. And so we start with the original size, and it's 4, right? So 4. Then we subtract the receptive field, right? Then we subtract the receptive field. And this is 3 times 3. So this is f, right? Our hyperparameter f, right? So this is so we're gonna subtract 3, right? And now we're gonna add 2 times our zero padding, which is 0. We don't have zero padding, right? But this will be important when we have zero padding. And then we divide it by the stride. The stride is 1, right? So stride is 1. Okay, cool. And then we have it, that is fairly simple. And then we add +1, right? So, and that's it. So we get 2, right? So this means our feature map is size 2 times 2, which is correct. Okay, pretty easy. Now, okay, I want to convince you why zero padding is a good idea, or why we usually do it, right? So the first problem is that if you look at the feature map, right, when we extract something, so when we extract something right here, so for example here we extract this thing right here, pop, 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 pop. When we extract this right here, it's basically it centers around this pixel here, right? So it says, okay, what's the environment of this pixel, right? So it centers around this pixel. That's just how it is, right? Because we take all these values and it basically says, hey, what's around this pixel? This is the center of our filter. The problem is this neglects the edge totally, right? So I mean, this is present, but we don't have, like, if there's something important here, we rather miss it, right? And another thing is that our feature map here is pretty small. It gets pretty small here, right? So and so the basic idea is that we have some kind of information loss that we want to avoid. So what we do is, it's pretty simple. Actually, the idea is to make the image larger, right? And apply the same filter, but with nonsense information. So what we do is we just put zeros around it. So I want you to think of zero padding as putting a frame around it. That's it. Okay. And the frame size is P, right? So if we put 1 frame around it, it's P equals 1, right? Here we have P equals 1. That's 1 frame. If we can also say, hey, I want more frames around it. So then it's P equals 2 and so on, right? So if we have 1 frame around it, it's P equals 1. If we would have another frame of zeros around it, right, then that's P equals 2, right? And now let's do the same thing. So you can see the values have not changed. So we just put it around this image. So these values, of course, have not changed. The same thing, right? So the zero padding also technically doesn't change the input image, right? It's just put around, right? So, but what we do now is we don't start here, but we actually start here, right? You can see this, what we do. Oh my God. Actually, detects my handwriting. So we start here, and now it's centered around that corner. You can see this, and now we get more information about that corner. Isn't that cool? Yeah. And also our feature map, our resulting feature map is way larger, right? We didn't change the receptive field. It's still 3 times so. We just activated zero padding and did nothing else. Everything else constant. Stride, everything else constant, okay? Okay, let's have a look at how this affects our calculation. So same idea, right? We have the size is 4. I will show you a trick, right? The input size of the original image, and we still get this is the original input size, is 4, right? So now you have 2 approaches. You can use the stupid formula and say, okay, we have -3, blah, 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 because this is 3 times 3. And then you have 2 times P, which is 1, right? which you can do. But actually, what it means is, what does it mean? Like in your brain, what you do is you just look at this as the new input image, right? Just look at this as the new input image, right? And now you count 1, 2, 3, 4, 5, 6, right? 1, 2, 3, 4, 5, 6. So this thing now is actually 6 by 6 now. And so what all we do is we actually change this. So this is the one approach. We can use this and we can divide it by 1 and we have plus 1 and we have 4 times 4, right? But also alternatively, we can just count this and say, okay, it's actually 6, right? So this is 6 by 6, right? This is 6 by 6 minus 3 divided 1 plus 1 is also 4 by 4. So we just change, actually in your brain, you can say, okay, we just change it. You can just picture. The only difference is that that this is artificial. We don't really change the input image. So we do it as a computational step in Python, for example, right? So we don't really change it in pre-processing, but we change it in the actual learning of the neural network. And that's all, right? It's just a technicality. But if you have problems with this, just think we just made it larger. That's it. That's zero padding for you, right? So if you want to use the formula, you can use the formula, so whatever you want. So here we have another example, right? So for example, if we have a real filter here, so this is the filter, and then you can calculate the feature map. And so this is just the convolution. So again, we are in step 2 now, where we say what happens mathematically, and we look at the convolution layer. So basically, what if our 3 times 3 filter, so this thing right here, is actually that thing, right? So basically, this thing right here, if these are the numbers in here. So, and then what we do is we just multiply these numbers. So here you can see we have the first field right here, this one. We multiply, so it's 0.3 times 1, 0.5 times minus 1, 0.9 times minus 1, and so on. So you can see it here. It's element-wise multiplication. This is very important. It's not, I repeat, not matrix multiplication. This is not algebra. It's point-wise. So see the point here? This is point-wise multiplication, which is super easy, right? You just multiply this with that with that, and so on. And that's it. And then you get this result, right? And then from there on, you can just calculate this result. And from this one, you just get the value of the feature map, right? And this is the second filter position, right? And then what you get is the 2 by 2 filter. So this is without zero padding here. So P equals 0. And we get these values. And you can see here, I decided to do the simple thing where we add up all these values. So we add up these values, 0.3 plus, or in this case, minus 0.5, minus 0.9, and so on. So I just add all these values up and divide them by 9, right? So I get an average value, how important this whole thing is. And the same here. And if you want, you can calculate the other two positions of F3 and F4, and can report back to me if you like. Okay. So just as an example. Okay. But this is rather easy. So this is what you could do like in the exam. As I said, this divided by 9 is not always done. So sometimes it's just the sum, and then we do batch normalization, right? So in the exam, since both can be done, I don't care if you just add them up and say, hey, I'm going to do batch normalization after, but then you have to write it, right? Or you do this for the simple exercise. Just we have to keep the size down a little bit. We can't have these large values because it will hinder optimization. That's the main point. Okay, now this is just a little bit optional, but it's for your understanding, right? So it's not, is it really optional? Well, I'm not going to give you an image like this in the exam. However, it's good of you if you understand what actually is, and if you do Power BI or something like this, or you know exactly what I'm talking about. So as I said, these inputs, they are usually 3D. Like here, you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, I think. So it's 10 times 10, and we have a depth of 3. So it's 10, 10, 3, and we can put it as a cube. And then we can say, okay, we put this into one value in the feature map, and we get a feature map like this, for example, right? And another thing, like we can hear padding. So we have padding. Here's padding explained. So this is zero padding. We do a frame around it. This is just another visualization of what we've already learned, right? So it's not really hard. I just want to show you this because in some papers, these 3D visualizations are standard, right? And for some people, this might be easier to understand if they see it in 3D, right? Yeah. And to basically see what kind of what convolution do. So it's kind of the idea of business intelligence. We look at it and we extract a report out of it. So if you will, the CNN is basically business intelligence based on images, right? But we don't say what we extract, but we learn what we extract, right? So it's automated. But it's slicing, dicing, and so on, right? So another thing that is pretty cool, I want to briefly discuss is 1D convolution. This is just if we have multiple channels, and this is what we actually kind of do in the CNN explainer, right? So it's kind of, so this is our image, right? This is width and height of the image. So the dimension of the image is still the same, as you can see here, but we average over all the channels, right? So sometimes we do that. So, and this is what we usually do if we have these 3 RGB channels, right? So in the explainer, it's like RGB. So this is the image in R, this is in G and B. And then for each of them, we have in the first convolution layer, so convolution layer 1, we have for each of these, right? So this is filter 1. So we have filter 1. For each of these, we have an own filter. This is very important. So we don't have one filter, but we have filters, right? And then what we do is we just add them up, right? We add them up and we add a bias term to this called B. So basically B, and then we end up with the same size here. And so this value right here, I'm going to show you how this value comes. So this value is, let's say this value is A, this value is B, and this value is C. So this is the first value, right? And this value is A plus B plus C plus the bias, right? So plus the bias. And this is what we do here, right? So this is the value here. So we get a little bit of these, and then we have a kind of offset. And this bias is unique for each filter. So this bias is the same for filter 1. But if we have a filter 2, there's a different bias, right? So it's a different bias term. So we have that many bias terms, the same number as we have filters. Why is that? Because if we have multiple filters, so we have F1, F2, F3, so these are the neurons in the convolutional layers. So each filter looks at something different. And this bias, as we have learned in ANN, it's this exact same thing, gives us some kind of offset and can move the importance of each filter around a little bit, right? So it helps us. This is why we usually in normal CNNs, we use this bias term. If you don't understand this, look at the CNN explainer, please, right? The CNN explainer is pretty cool in doing all this stuff, right? And you will see how this is calculated, how they do it, and this is how it usually is done. Okay? Pretty cool. So now after we've done this, so this is like zero padding. Now we go into the calculations of some other things. So we're going to go through the calculations of the other layers. So as we've talked about, the convolution, I think, is pretty clear right now, right? So again, here you can see the example right here. I've written it out for you. Then we divide it by 9 and we get this value. We get the value of 0.55 and we put it here. So I've done this for 2 different positions. for this position in the feature map, for this position. And if you want, you can do it for all the other positions. So for example, you can start here and calculate it and see if you can get this feature map. So this is your practice. So you have the results, so you can practice, right? So you just have to move this filter around this image and get these numbers. And this is how you can practice, right? So you can practice 1, 2, 3, 4, 5, 6, 7 times 7 times. Okay, pretty cool. Okay, now what we want to do is we want to practice also a little bit, and we want to practice we want to use this example to again practice what dimensions do we get, right? So the extent of the dimension. This is very important to manage what's our output and what is not our output, right? So again, and here, so we have a 3 by 3, and we have an input of 1, 2, 3, 4, 5, 6, 7, 8, 9, right? So we have 9 by 9. And so we want to see how large this feature map is. And if you want, you can do it with me, right? So I've, of course, written it down. So in the lecture notes, you always have my thoughts on this. And so we have it here. So, but the idea is that we start out the feature map size. So I'm going to do it on parallel. So we're going to start out. So the width is the height. So the width of the feature map is the height of the feature map. If you want, I have done it a little bit more professionally here. You can say, okay, W1 is 1 because of the first layer, the input layer. Then the width 2 is the width of the CNN, and you can number them through if you like, right? So I've done it more professionally here in the explanation. But so the height of the feature map, this is the same, and we're gonna start, right? So we have the size, we have 9, which is pretty cool. And then we subtract 3, right? Which is 6. Then we have no zero padding. 1 plus 1. So this is 6 plus 1. This is 7. So we have 7 times 7, which is our output, right? 1, 2, 3, 4, 5, 6, 7. Okay? Practice it. If you don't understand it, practice it. This will be in the exam. I can guarantee you almost, right? Because it's easy. And if I said, try to use the CNN explainer here. It's so cool, really. It is such a good tool. And it will show you how it works. Like the thing I just explained, that we have 1, 2, 3 filter matrices. So this will be important for the number of parameters that we have, right? And then we add them up, and we add the bias to it. So we add these values up. So we add this value, this value, this value, we add them up, right? So this is why the plus is here. And then again, we add a bias term to it, right? You can see the bias term. If you hover over it, you can see the actual bias term that is added up, right? And then we get this value right here. So this is like the result. Okay. Now, it's easy to calculate the size of the feature map. Another thing that we have to learn to calculate is the number of parameters. And yeah, okay, this might be a little bit hard. Okay, so I'm gonna make it really easy, right? So I'm gonna make it really easy, and I'm gonna do it later. We're gonna do it later. Now you have it here. You have it here if you want for this example, but I'm gonna do it later. I'm gonna do it in the third step where we have this. This belongs to the sizes and the things. So I'm gonna do it in the third step because it makes more sense and the explanation is better there. Okay, so we're gonna go to the calculation of the pooling layer. I think the pooling layer is so easy to explain. I don't have to do it again, right? So here we have a max pooling layer. Just for fun, okay? If I don't give you the F and the stride of the pooling layer, can you guess it? Here. Just guess it. How do we get this size? Like, obviously it's given here, but you can easily, usually the pooling layer has a larger stride. So usually the stride is 2. And yet the receptor field is also 2. So we have 2 by 2 receptor fields that we just move along, right? That we just move along. And again, we have this. We cannot forget about this. And then we get this. We already spoken about it. Okay. So that's it. We just take the max. And I think I don't have to explain it again. Now, let's also calculate. Here now we can also calculate the output dimension, right? So again, what's the input? The input here is 7 times 7, right? Input is 7 times 7. And now we have F2 and S equals 2, right? So, and what we get is the same formula. Now the only difference is, so we have no zero padding. There is no zero padding in max pooling. Like we can, this is why the formula doesn't even have it here. It's pretty easy. But now the important thing is that we divide by the stride, and the stride now is not 1, but 2. So we get 3.5, and we always round up to the next integer because it makes sense. We cannot have 0.5 fields. This is just ridiculous, right? Sorry. So we get 4.41 as a result. And this is it, right? So we get the pooling, and so we get this thing 4 times 4. And this is what we get, right? So the ReLU layer, as I said, all it does is it changes all the negative values to 0, and that's basically it. Okay. So now, so you can see here what we actually do for this example. And this is pretty cool. Now what I want you to do is I'm going to give you, like we have enough time, I'm going to give you 2 minutes and you think what would be better. ReLU first. It's like we have the convolutional layer, right? And then ReLU first or max pooling first. And then, like what's the best thing? You think about it, I give you 2 minutes, I'll be right back. All right. So what do you say? Now, of course, there is a small hint here, right? So that the result actually is the same. Obviously, like if I first do that, or like if the max, like if I take the max, for example, I will disregard a lot of negative values anyway, right? So this is pretty cool. But then again, if I have, for example, where there are only negative values, then the ReLU will help, right? So, so technically, it's better to first subsample through max pooling because max pooling will get rid of a lot of numbers, right? A lot of negative numbers, and then apply the nonlinearity, right? So which is ReLU, right? ReLU is nonlinear, right? It's not a linear function. Okay, so if you want to discuss it, you can look at this right here. So I've give you some links that discuss this. And yeah, that's basically it. Now it's important that we repeat this layering like here many times. And then At the end, we get something like this, and this we put into the fully connected layer. You can see it right here. So the fully connected layer, there is no calculation. So the fully connected layer, the first step in the fully connected layer is the flat out, right? And then we have, so it's wrong that in the fully connected layer there is no calculation because it's a neural network, but the first step is just to flatten out. And then we have a normal neural network. Like it could be either something like this, right? We could also have a hidden layer in between, right? We can have multiple hidden layers in between, right? It depends on your design, right? But the thing is, what we have in the end, so this would be just a logistic regression, what we have here, right? So in my example here, without the hidden layers, we have a direct connection from the flat out input to X or O, right? So if we have direct weights, we just have all these variables here. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 variables. So we have 12 weights on the variables. You can see the larger weights here with the larger positive and negative weights. And that's it, right? And then we get the output here. And we get just simple values of the output. So for example, we put an image in and we get a value like this. And this tells us, hey, it's an X, right? And that's it, right? So at the end, it's a normal classification, just like we've learned. That's it. It's the magic actually happens here, right? So this is actually the new thing that we learned. This is the new thing, the really new thing, and everything here that happens here, right, from here on, so this thing right here, this is not new. This is just A and N that we had before, right? And this is how you need to imagine this. And I think this will help you out a lot, right? So, and then putting it all together, it looks like this. And now let's put it all together. So I have prepared another example. So we are now in step 3, where we really want to get our calculation on a little bit, right? And what I have here is like, what are hyperparameters and parameters? You can read through this, or before you read through this, I imagine you would want to think yourself. Like you should realize that yourself. Like, of course, I give you in the lecture notes the ideas, but you should think of it before you look it up, right? It will help you out understanding it. Okay, now, sorry, really bad cough today. Okay, let me see. Where do we have it? Okay, there we go. Okay, so I have prepared an exercise sheet for you, right? It's called CNN exercise calculation. You will greatly benefit from this in the exam as an exam preparation, right? So I uploaded this before the lecture, shortly before the lecture, so you wouldn't have like the large chance to study it. So you listen more or less to my explanations. And the thing I want to focus on now is not the activation size, but actually the parameters. So let me just make it a little bit smaller. Yeah, this is okay. This is better. Okay. Okay, so we see more. Okay, so now this table contains a normal form. So sometimes the summaries also in Python, as you've learned, maybe. Let me just get a pen here. You see that this one right here. So we have a layer. So this is the structure of our network, right? This is the architecture of our network. So architecture, and this is obviously given, right? So the architecture is given. So we start, we're gonna go from top to bottom, right? Now I'm gonna explain everything. Okay, and our specific task now is to pay attention to how we calculate the number of parameters, because this is what we haven't spoken about. Okay, so the activation shape and the activation size is just the multiplication of this. So if you think this is something new, it's just a because we need this number later on, but it's okay. So input layer, and here we have the activation shape. So this is the dimension I was talking about. This is always like three numbers, and this is the activation shape is the dimension. Usually, this is the size of the layer, right? Or the size of the output of the layer, right? But we call it activation shape because it's more general. For example, for the fully connected layer, we don't have really a feature map because it's flat, right? But we have an activation shape. Okay, so activation shape is size of the feature map, whatever you want to call it, right? So the input is given. There's nothing we can do about it. The input is always given. This is just the image size. Okay? This you will always have. There's no way around it, right? I could make a sneaky exam question where you re-engineer this, but usually this is given. So we have an image here of 32 times 32. How many color channels do we have? Is this RGB, gray, or black and white? I want to know from you. How many color channels do we have here? Is this RGB image? Like this is the width and this is the height. But is this RGB? Yes. Yes, it is. Yeah, because of the free. You can see it from the free here, right? So we can see that this is RGB, right? Or it has some other weird free color channels, but at least we have three input channels. This is very important. So this means we have a cube structure. Okay, so our example, this black and white example had here the number 1, right? So, and it's important because we need this for the number of parameters. We don't need this for the activation size actually, right? So the activations for the activation shape, we don't need this, right? Because the shape is just width and height, right? And this. So, but we need this for, so we don't need this for the size of the feature map, but we need this for the number of feature maps, obviously, right? Okay, let's go on. So now activation size parameter 0. There are no parameters in the input, right? The input is just an input image. So now, second, the first convolutional layer. And I've written the hyperparameters in parentheses here. So, and this we need to study. So we have f equals 5. This is the spatial extent of the receptor field. So the spatial extent of the filters. We have stride equals 1 and we have d2 equals 8. So d2 equals 8. This here is actually the number of filters. It's just the number of filters, okay? That I have. The number of neurons, the number of filters, the number of experts looking for. So the first looks for this, the other looks for this. So how many do I have? This is simple as that. So we calculate this the same. So height is always the width. So you know this formula. We have no zero padding. I said here there is no zero padding. So some things are assumed here. A thing I forgot is we also assume a bias. We assume a bias. I will also write this, of course, in the exam, right? I will write the assumptions down. And for all shapes, we have height equals width, so they are quadratic. I could also write shapes are quadratic, whatever. And then this formula you already know, and we have an output of 28 times 28, and we have 8 filters. So we have 28 times 28 feature maps as a result of this convolutional layer. But now, so we know this. Like if you don't know how this is calculated, we've done all the time now. Now the problem is how many parameters do we have, right? And this is somewhat tricky, right? But I'll show you a way that how it's not tricky. We go from the inner to the outer, right? So the first question you ask yourself, what are parameters? And you know, we only have parameters basically in the convolutional layer, right? We have the bias, okay, and we have the receptor field parameters. So basically the parameters are the values in our filter matrix, right? If this is our filter here, these are our parameters, right? 1, 2, 3, and so on, right? So these are our parameters, right? So, and all these parameters we need. So at least for each filter, we have 5 times 5 parameters, right? For each filter, our filter size is 5 by 5, so larger. So we have 5 by 5. So we have 1, 2, 3, 4, 5, and 5. So this means we have 5 times 5 equals 25 parameters for each filter. Remember, a filter is, we're looking for a certain thing, like, for example, this or whatever, right? So, and now how many filters do we have? Well, it's given in the hyperparameters. We have 8 filters. So, however, we have 8 of these filters. However, now comes the tricky part. As I said, we're gonna need to start here. And so the problem is, now each of these filters, right? 5 times 5 is 25. The problem is, for each filter, we not have 1, but 3, because we have 3 color channels, right? Remember, we have 3 color channels. R, so we have an R, G, and a B image. So we need this thing. We need 1 for R. We need the same thing for G. And we need the same thing 5 times 5 for B, right? And it's always 5 times 5, right? We need different values, right? So we need 25 times 3. So this is because of RGB. This is because of the input. This is because of the input channels. Now, usually this is 1. This is why we don't care. Usually it's 1. But for us in RGB, this is 3. Okay? Now, and how do we calculate it? Well, I've put it here in the image, right? So you can see here, these are the 3. So this here in our example, this is 5 times 5, 5 times 5. And actually in the example, in the CNN explainer, it's different. So it's not 5 times 5, 5 times 5. But in my example, it's 5 times 5, right? So we have 25. We have 25. We have 25 different parameters, right? And we have the bias term, which is 1 more parameter. So we have 25 times 3 plus 1, right? With 1 bias. And then we have our filter number 1. And this is filter number 1, right? So we have 25 times 3, because 1, 2, 3, plus 1. The bias is the plus 1, is the bias, right? The 3 is because we have 1, 2, 3, and the 25 is obviously because 5 times 5. So, and now we don't have 1 filter, but we have 8 filters. So we multiply it by 8. And that's it. That's the number of parameters, and it's 608. So this, you have to don't learn it by heart. It will go wrong. You need to understand it. You cannot learn a formula by heart. I mean, you can potentially, however, understand it. Please understand it, okay? So let's see, we have a question about it. See? Could you please clarify again which ones are we considering filters and which ones features? Filters and features. Okay. A filter. Okay. Let me see. Okay. Here, let me do it here. So this one here. So the question is, what is a feature? What is a filter? Okay. So feature is everything that comes from the input, right? So the features are the pixels here, right? These are the features, right? The features are the pixels. We cannot change the features. So features in the input layer are pixels, pixel values. The filter is this matrix that looks over the features, that looks over the pixels. This is the filter. And the result of the multiplication of this and that is the feature map. This is the feature map, right? So basically, the filter is the inspector looking for one thing. I'm not going to call it feature, looking for one. You can also call it like higher ranked feature, whatever, looking for one thing. For example, the filter looks for a diagonal, right? So, and then it reports back with high numbers in the feature map if it occurs at that position or not. That's it, right? So, features are pixels, filters are the thing we train. So these values here we train. These values are parameters that we train. The input image is given, and the feature map reports back, hey, do we have this thing here present? Right? That's it. So you can also say basically what we also say the thing we're looking at. So this thing right here is also like kind of a feature, right? Because we generate features. This is what we do. We generate higher ranked features. So the smallest feature we have are the pixel values, right? And then we go to higher ranked features like, is this present? And then we go to higher ranked features like, is something like a face present, right? So this is a feature is just an indicator that we need for classification. So we start with the basic features, which are the pixel values. Then we apply filters that report in the feature map, hey, is this higher order feature there, right? I hope this clarifies it. Now, the important thing is you have an input image, right? You start with an input image, then you put a filter on it, then you get a feature map. Then you do the same thing again. You're gonna make a convolution, but you do the convolution not on the input image, but on the feature maps, right? And the beauty of it is then you look for things, then you look for a combination of these higher ranked features, maybe a circle and something like this. And this you can enable this because you already have neurons that look for these things, right? And then you can like combine them. And that's it, right? So that's the idea. I hope this helps, right? So important also is the idea on what are hyperparameters and what are parameters, right? So, but this you should learn. Okay, let's go on. Pooling layer. Again, pooling layer, pretty easy. We have stride 2, F2. So the important thing is in a pooling layer that the number of filters, of course, they do not change. Like we pool every feature map, right? So if we have it here, like we pool every feature map, right? So if we have 8 feature maps in our case, so filter feature map 1, feature map 2, feature map 8. We also have, of course, 8 smaller feature maps after the pooling, right? So this doesn't change. So the extent here is then we go from 28, 28, 8. We just half it, right? We go from 14, 14, and 8. That's it. So parameter 0. We don't have parameters in the pooling layer. As I said, there are no parameters in the pooling layer. You can also see that I don't even added the rel-u layer because the rel-u layer, we could like add the rel-u layer here if you want, but the rel-u layer doesn't have any activation shape because it doesn't produce a new shape even, right? The pooling layer does produce a new shape, but the rel-u doesn't even produce a new shape. It belongs, but it's just a mathematical function is applied. If you want, you could write it down here and say, hey, we're gonna add the rel-u after the pooling, but the rel-u doesn't really have parameters nor an activation shape, and then of course also no activation size. Now it gets more interesting, and this is the last thing we want to do. So convolution number 2, right? Same thing. We have, I called it F2 here. So we have 5, 1, and 16. This time we have 16 filters. So, and we're interested in, we can again calculate the size here. So we have 10 and 16, of course. But more interestingly is the number of parameters here, right? And we do the same thing again. we do the exact same thing. It's very important. Do the same thing. So you see, okay, we have again size 5. So we have the filter size 25, right? So, but now the input is not free. We don't have free difference, which was the input in the RGB right here. But now the input is the result from the last pooling layer, right? Which has, let me see, oh yeah, it's 8, right? We have 8 here because here the output of the convolution layer, we had 8 filters, and now we basically have 8 images that we have to look at. Now, we don't look at images now, but we look at the feature maps, which are kind of images, like heat maps. And now, very important. So we do the thing that we do here, right? You can see this right here. So this was with an input image. And now you can see here, we have 8 outputs. 1, 2, 3, 4, 5, 6, 7, and 8, right? We have 8 outputs. So what here was 3, we now need 8 for each filter. So this is like the other thing. So this is the convolutional, the second convolution layer. This is the first filter and the second convolutional layer. So for each filter, right, we now need 8 filter matrices. 1, 2, 3, 4, 5, 6, 7, 8, right? And then they again get added, and we again have a bias term added to this. And this we need to do again 16 times. Now here we have 16 filters, right? So it's always input and output, right? So here we have 5 times 5, right? So it's still 5 times 5. So we've 25 parameters because it just says so here. And the important thing is we need to apply this 8 times, right? But different. So we need different parameters for each of the features, which makes sense. You don't want the same. Like some of the features before, so maybe this looks at something like this. This looks maybe at this. This looks maybe at something like this. This at something like this. This has another triangle maybe here. This has maybe something like this, and so on. So we want to check if other features are present here, right? And this should be for each of them should be an own thing, and then they get like added up and with a bias term, and then we have other filters. Now this looks for something in all these images, and this looks for something because we want a higher hierarchy feature, right? So we need the opportunity to add these things up, which is done exactly here. So we add these values up and then get here the higher order features by adding this up. And this is the cool thing, right? Yeah, and then times 16 because yeah, we have 16. Now we have to do the 16 times, right? Don't forget there's a bias unit here for each of the 16, right? If you don't like this +1 in parentheses, right? You don't know, why is it here? I think this is the better thing, but you can also just say, okay, for each output feature map, we need one bias, and you can just write +16 here, right? So you can actually do 3200 +16 if you like it better, right? You can just add this if you like it. Okay, pooling layer, no parameters. Okay, easy. And now comes the last thing, and the last thing we already know. The last thing is just the number of parameters in a neural network, right? So the important thing is the activation shape is now set by us. Now the fully connected layer takes the last pooling layer, takes the flat last pooling layer as an input, right? So how many values do we have in our flat vector, right? So what's the input here? So this is the input for FC1. And so basically it's a vector of the size, well, 5 times 5 times 16, which is 400. So we have element 1, element 400. So we have 400 elements that gets flattened out. And now what we have here is here you can see what we said here is, okay, we have 120 neurons. Now, 1, 2, 3, 120 neurons. So this is a standard ANN, a fully connected ANN with 120 neurons. So this is fully connected layer 1. And then we have a fully connected layer 2. So here again, we have 84 neurons, right? So we have 84 neurons here. 1, 2, 3, 84. And then we have softmax, which is basically our output layer, right? Softmax, this is output layer. Output layer, I'm gonna draw a little thing around this. And this has 10, because we have 10 classes. This means we have 10 classes. 1, 2, 3, 4, 5, 10. We have 10 classes, boat, face, whatever, right? So that's it. So we have 10 classes. So this is a classification problem with 10 classes, right? And you can see, of course, this is always 1 because we have now a flat hierarchy. This is just a normal neural network with 2 hidden layers with 120 and 84 neurons in the hidden layers and 400 neurons in the input layer. So this is how I want you to imagine this. So we have 400 in the input layer, 120 neurons in the second hidden layer, 84 neurons, and then 10 in the output layer, which means we have 10 classes. Now, if I write to you in the exam, you have 10 classes. Now you know that this needs to be 10, right? And now we can calculate the number of parameters. And this is just the number of elements in our matrix from the ANN that we use to calculate. So how this is calculated, you need to know, because this is the same formula that we applied. Now, we start with the left layer, right? With the layer that we have here. Now, this layer has 400 units, and each of these 400 units is connected to one of these, right? But it doesn't have 400 because it has 401 because we have the bias, right? This is always 1 in a neural network, right? So we have 401 units that are connected to all the other units in the second layer. So for this, we have 400 inputs times 120 are 48,120. So these are the number of parameters. Remember, we are talking about these weights here. These are the parameters. And now the same thing for FC2. So the input are these neurons. So we have 120 plus 1 because we also have a bias unit here that is 1 and that is connected to all of the other neurons. So we have 120 plus 1 times 84 is 10,164 parameters. And then again, we need to connect this layer with our last layer. And here the same thing. So we have in this layer 84, but we also have a bias. Don't forget the bias. Times 10. Because we have 10 outputs, and this is 850, and this is what we have. And what you can see and what should surprise you is, look, that's the fully connected. So the actual neural network, although we have shrunk it down immensely, right, to 400, right, now has also all in all the parameters, so most of the parameters come from the fully connected, right? So this should show you that actually using an ANN from the beginning would be very bad, right? But we will have it in the end. And also, this is a nice exercise. If you have some questions, let me know. We will go through this once more at the beginning of the next lecture. Next lecture will be in person again. But I wanted to record this, specifically this example, so people can rewatch it. You have an explanation here. You have the explanations here. And I would suggest you go into this CNN explainer and just think about, hey, what are the number of parameters here? So your homework should be you calculate the number of parameters and the output sizes in the CNN explainer, right? Because this is not 5 times 5, right? I just used the explainer image for this example, but actually the sizes are quite different. And you try to figure out the number of parameters if it's possible. I'm not sure if you have all details, but maybe you can re-engineer and think about it a little bit and it might work. So this is your best way of practicing, is using examples and just practice this. Okay. So next time we will sum up CNNs. We will also talk about other forms of layers that can be added. So I briefly talked about the batch normalization. We will dive a little bit into this, and then also the dropout. I haven't talked about this at all. Spoiler alert, it is a regularization that avoids overfitting, but we will talk a little bit about that when we finish up CNN in the next lecture. And we're going to have some applications and some directions, some future directions where CNN goes, what we can do, and some other things that are pretty important around that. With that, I want to thank you so much for joining today. I hope you can use this also for exam preparation. I've uploaded the PDF, and if you have any questions, please, for now, we will have a question answering session after lecture. Thank you so much and see you next week. Bye, everyone.